Welcome everyone. This is the July 2021 National Hydrologic Warning Council webinar. I'm Brad Hallwagon from Wood Consulting. I'm also the NHWC Vice President. I'm hosting or moderating this webinar today. Our topic today is batteries and solar panels, and it's going to be put on by Mark Moore, who is an employee at Distinctive AFWS Designs, but he's also a NHWC board member himself. A few announcements first. This webinar will be recorded and we'll place it on our YouTube channel shortly after the webinar ends. We are looking at a way to make these webinars publicly available, mainly without additional advertisements. So you may see some emails coming out soon with a change in location for these past webinars, and that'll be the place where we put all the future webinars as well. We're going to keep everyone muted for this presentation. So there is a chat box or chat function that you can use to ask any questions as they come up. Also, as a reminder, for those that have CFM, you can get 1 hour of continuing education credits for CFMs through the ASFPM. When I send out the link to the YouTube video, I will also send out the certificate for those continuing education credits. One thing that I wanted to talk about today, since NHWC is an all volunteer run organization, we don't have any paid staff. We're always looking for folks to get involved and help out. And so there are several ways that you can get involved in the NHWC. The first is by simply becoming a member. There are numerous benefits to becoming a member, including national representation from an organization that is really focused on hydrologic warning. We host numerous training and education opportunities like this. We have our biannual conference and workshops throughout the year. Members get reduced fees on a lot of those. There are numerous other benefits, and so if you're interested in being a member, I encourage you to go to www.hydrologicwarning.org and check out the membership page. Now, once you become a member, there are ways that you can really get involved and help drive the organization. The first is the Executive Programs Committee. I'm the chair of the Executive Programs Committee as the vice president. That committee coordinates all of the technical activities of the NHWC. There are several subcommittees that revolve around the different functions within a flood warning system. The Training and Professional Development Subcommittee is one of those. We're the ones that put on these webinars each month. A Conference Subcommittee is another one of those. Standards and Guidance Subcommittee is one of those. So if you're interested in getting a little more involved in what goes on at NHWC, I encourage you to go to the website and check out our Executive Programs Committee page. It's under the About tab on the website. See if there's anything you'd like to get involved with, and just email me at brad.heilwagen@woodplc.com. Let me know. There's also an executive office, even though we don't have any paid staff, that coordinates all of the administrative activities that go on, the marketing, the newsletter, any press releases we put out, any legislative liaison, that's coordinated out of the executive office. So there are ways that you can get involved in those too. And I guess the last way that you could get involved, really drive the organization, is by becoming a member of our board of directors. We recently put out a call for nominees for our board of directors. That call is closed, but since we haven't had elections yet, there's still opportunity to become a member of our board. If you want to nominate yourself, simply just email me and let me know that you're interested. Another thing I wanted to point out, the Training and Professional Development Committee has put a lot of work into our frequently asked questions page on the website. So if you go to our website at www.hydrologicwarning.org, look under the resources tab, there's an FAQ button. And there are frequently asked questions posted on there revolving around Alert 2, rainfall, hydrology, stage, and just some general flood warning questions. You can get a lot of your questions answered about flood warning right there. So I highly encourage you to check that out. And if there are any questions that you may have, there's a way that you can actually submit a question through the website too. Okay, so this is our July webinar on batteries and solar panels. Our next webinar is going to be August 25th. David Leader from Hydrolinks is going to be talking about transmitting data once you collect it. So a lot of telemetry. And then for the month of September, Brooke Newland from Fenstermaker is going to talk about post-disaster data collection and evaluation. So if you'd like to register for those two webinars, I've already set up those registration pages. Just go to hydrologicwarning.org and visit the training committee page. As it stands right now, we are still planning an in-person Texas workshop for October 13th through 14th, 2021. It's going to be held at the Embassy Suites in San Marcos, Texas. They're working on the agenda right now. I don't have the registration page set up yet. Just keep an eye on your email for that. When the registration page does open up, we'll send out a big email blast. Just know that we are keeping an eye on the COVID situation and the resurgence in several states. So as things evolve, we're going to keep you all in the loop about what's going on with our in-person activities. Transmission newsletter. So you should be seeing in your email a transmission newsletter coming out next week. They're always looking for articles and interviews for that newsletter. As you can see on the screen, there are various topics that we like to focus on for the newsletter, and the interviews have been really good recently, where they interview someone from an established flood warning system to talk about what they deal with on a day-to-day basis and how they handle certain situations. So if you're interested in submitting an article or think that maybe you could be interviewed or have a recommendation for someone that could be interviewed for the transmission newsletter, you can email editor@hydrologicwarning.org. And then finally, and I've hit on this the last couple months, we're really trying to get our mailing list up to date. And if you're not seeing the emails coming from us on a routine basis, your email might be out of date. So you might be missing those newsletters as they come out or any other announcements that happen. If you want to make sure that your email is up to date, just email me at vicepresident@hydrologicwarning.org and I'll help you out. So with that, I'm going to turn things over to Mark Moore and let him talk about batteries and solar panels.
All right, thanks, Brad. I appreciate it. Can you hear me okay?
Yeah, you're good to go.
Okay. All right. Let me go ahead and get the presentation started. Can you see the presentation all right?
You bet, man.
All right. Well, I'm gonna get started into this. So this is the third time in a year I've been talking about batteries and solar panels. And I think the first time you give a presentation like this, you kind of end up being like, all right, that guy kind of likes batteries. And then the second time, it's like, man, that guy's really into batteries and solar panels. At this point, giving this presentation kind of a third time, I'm worried I might be getting a reputation as the batteries and solar panels guy, which isn't necessarily 100% true. I don't claim to be an expert on all of this, but what I have done is I've seen that there is a lack of information out there and some misunderstandings. And so we're going to cover a lot of that and kind of clear up some common misconceptions when it comes to batteries and solar panels. One thing I also want to kind of mention before I jump in is that, we can spend a dozen webinars talking about the most accurate modern sensors out there to measure rainfall and to measure stage. But at the end of the day, you've got to keep your sites powered. And unless you've got some sort of, plug into the local utility company, you're probably using some sort of battery and solar panel combination. And that's true regardless of what type of data you're transmitting. It could be, weather data, rain data, stage data. It can be sent on alert 2, could be sent on GOES, it could be sent on a cell modem, on satellite. All of these systems almost always have the same battery and solar panel combination in common. And it is kind of the core of what makes these systems work, because if you don't have power, you're not going to get data, you're not going to transmit, you're not going to have accurate information, and you're not going to do flood warning. And it's an often overlooked aspect of design and system maintenance. And so as we go through these slides, I just hope that the intent, you guys that are watching, you really start to think about the fact that, well, I've always just put in batteries, but what do the numbers actually mean? So with that kind of rant, I'll go ahead and get started. I can click the right button. All right, so here's the very basic overview of what we're going to talk about. I haven't timed this out. I don't know if it's going to be under an hour or over an hour. I think if I talk about batteries and solar panels for over an hour, people aren't going to want to listen to me anymore. So I'll try to keep that under that hour. If you guys have questions, feel free to put them in the chat. And then Brad, if there's a really topical question, feel free to jump in and interrupt me, but otherwise I'll answer any questions at the end. All right, so the overview, what are we going to be talking about today? Well, we're briefly going to go over how batteries work. We're going to talk about what all these numbers mean, how you can test a battery, the proper battery maintenance. We're going to talk a little bit about solar panels and what is power, what being a little joke there, and then just some final comments. A quick disclaimer before I really jump into it. A lot of the graphs and images that I'm going to use when talking about batteries come from the PowerSonic manual. It's a really, really nice manual. It's like 30 pages just talking about batteries. So if you are interested in this, I think it's worth downloading from their website. The other thing is that you're going to see some products from various companies out there. This isn't necessarily meant to endorse, but it's also not meant to discourage any of these products. I'm really not showing you guys anything that's bad or top of line. It's just these are the products that I've kind of worked with in the past, and just be aware that that's what they're in the presentation for. So some terms to know. If you pull up a battery, if you look at one that's on your desk or you look at one that's in a gauge, you might see some of these things on it. One is the AH, which stands for amp hours. Amp hours is actually the size of the tank. It's how much juice that battery can provide. In a way, I'm going to go back to this car gas tank analogy a lot coming up, but in a way, it's kind of like the size of the gas tank. So, a pretty typical one for an alert system might be a 12 amp hour battery, and a bigger battery might be a 100 amp hour battery. So the higher the number, the bigger the capacity of the battery. The next letter you'll see a lot is C, and it's actually a little confusing because it stands for capacity, but it's often used for capacity rate, or the rate of discharge of a battery. And so if you have something like a 10 amp hour battery, 1 C of discharge is 10 amps. And again, that can get kind of confusing, and we'll talk about why that's used in a little bit. But know that if you see the letter C, it's usually talking about the actual rate of discharge. V stands for volts. That's the potential of the battery. That's how much work it can do. And DC is direct current. And that's what all these batteries that we're going to be talking about are. You don't really see much AC when it comes to this line of work. And DC and AC don't really mix in the way that you might think they might. But just know that any type of battery or solar panel we're talking about today is a DC. Couple more things, a cell. So batteries have cells, individual cells in them. It's kind of like a building block of a battery. And that's typically somewhere around 2 volts. So a 12 volt battery is made up of 6 cells. Discharge is just drawing current from the battery. I'm not talking about flow discharge, I'm talking about battery discharge. So that just means that, how much current are you drawing from the battery? We'll talk about battery cycles. The cycle of a battery is a charge and discharge, basically one charge and one discharge of the battery. And the last term I'm going to throw around a little bit is sulfation. What sulfation is it's a formation of this lead sulfate on the actual battery plates inside the batteries, not like on the outside, but on the inside. And that's kind of what starts to happen to batteries as they get old and become less efficient. So discharge. When I said discharge, that's when the battery is being used. This is not a chemistry class. I'm not going to go over the chemical reactions necessarily. just know that when the battery is being used, you have basically a chemical reaction that's going in one direction. When that chemical reaction goes in one direction, it releases electrons that allow the battery to do work, that allow your gauge to get powered, to take PT measurements, to measure rainfall. This is the discharge. And when it's charged, the chemical equation just goes in the other way. And so what happens is that lead sulfate in the water that's in the battery, they're turning into lead dioxide, and sulfuric acid. And so it really is just a chemical equation that goes one way or the other if you're charging or discharging. This is something that pretty much anyone that's worked with batteries is probably intimately familiar with. What it does is it shows you the voltage relative to the percent rated capacity. And so if you were to take your voltmeter and you put it up against a battery and it says it's at 12.8, I'm not sure if you can see my mouse, but if you can, 12.8 is right around here on the graph. And if you move your mouse over, that's about 95% rated capacity. So a battery that's reading 12.8 is pretty much a full battery. However, that doesn't necessarily tell the full story. In a way, batteries can keep themselves running forever with the proper charging and discharging, kind of like your car tank, right? If you're driving around your car or your work truck, it gets low on gas, you fill it up, and you can keep moving with it. And in a way, a battery is kind of like that. You know, it's got this charge level, and when the tank's all the way at the top, you're reading at 12.8, and when the tank's all the way at the bottom, you're reading at like 11.8, 11.7, and you can refill it and get a fully charged battery. There's one problem with that analogy though. When you're draining or filling the tank too fast, when you're draining or filling a battery too fast, it will actually discharge O2 to prevent it from being damaged. And that prevents the ability for that equation to keep going back and forth as much as it used to. What happens is you get sulfation on the plates of the battery, and so the tank size of the battery is reduced every time you charge and you discharge it. And so, you know, going back to that gas tank analogy, imagine if every time you filled up your truck at the gas station, you put a marble in the tank. You've effectively made your tank smaller. And it's not by much, but imagine if you did it every single time you're at the gas station. By the end of your truck's lifespan, it might only have a capacity that's a few gallons, because when you go to the gas pump, you're filling up the tank, but the tank's mostly marbles. Knowing that there are many hydrologists watching this and hydrologic technicians, I went ahead and put a stat gauge on your gas tank. And that's really what's happening when you're looking at the voltage of a battery, is you're measuring what the water level or the fuel level is of your tank. And if there's a bunch of marbles in this tank, you're going to have less gallons of gas in there, even at the same level. And so when you're looking at that voltage coming off a battery, it doesn't really tell you the capacity, it more tells you the percentage that it's full. So if this gas tank was completely full of marbles and it was all the way at the top, yeah, it might be 100% full, but the fuel capacity is really only about 3 or 4 gallons. So coming back to this chart, I said that if you're at 12.9, you're at 95%, 90% rated capacity. That's rated capacity if it's a good working battery. Another way to think about that, just in case that wasn't clear, is it's a lot like water pressure. And so if you look at these 3 different cups, you've got a cup that's got a lot of volume, a cup that's got a little bit of volume, and a cup that's got barely any volume. Well, if you're going to actually measure the water pressure on the bottom of these 3 cups, it'd be the same because they all have the same water level. And that's what voltage is telling you. It's only telling you the water pressure. It's not actually telling you the water volume. And so if you want to know if you have a good battery, you can't just measure the voltage because it's not going to tell you the whole story. So, in summary, how do you test a battery? Well, voltage only says how high the gas is. It only tells you how filled your tank is. It doesn't actually tell you the volume in the tank. And so the only way to really know if you have a good battery is to empty it and refill it. And that's how you test batteries. It's called doing a discharge test. And what it does is it measures the total capacity or amp hours of a battery. And if you discharge it relatively slowly, and it comes back saying that it's within or above 60% of its rated capacity, that's generally considered a good battery. And this number is pulled from that PowerSonic manual, that's 60%. So if I've got a 100 amp hour battery and I do a load test on it, a discharge test on it, and it comes back and the discharge test says, well, I pulled out 80 amp hours from your 100 amp hour battery, that's still close enough to that good range that it's considered a good battery. So now that we've kind of talked about how you test batteries, I did say that we were going to come back to that pesky C that can be kind of confusing. So C, or sometimes called C rate, is used to express a discharge rate using the battery relative to capacity. So I'm going to throw some examples in here just to make it a little bit more clear. I'm using 12 amp hour batteries because that's a pretty common battery used for alert and alert 2 gauges. A 12 amp hour battery discharged at 0.1 C is 10% of C, so it's discharging it at 1.2 amps. At 0.5 C, it's discharging at 6 amps, and at 3 C, it's discharging it at 36 amps. We're just taking that number and we're multiplying it by whatever's in front of the C. So a quick question would be, if you have a 100 amp hour battery and you're discharging it at 0.25 C, what is the current that you're drawing it down at? And I used easy numbers there so you can do it in your head, but I'll give you a second to think about it. You have a 100 amp hour battery and you're discharging it at 0.25 C. That's discharging it at 25 amps. So why not just say 25 amps? Why am I bothering to say we're discharging it at 5C or 0.5 C or 0.05 C? The reason that we use that C rate, that discharge rate, when we're talking about batteries is because regardless of the size of the battery, batteries tend to behave similarly at similar Cs. So if you have a 100 amp hour battery or you have a 1 amp hour battery or one of these tiny ones, if you're discharging it at 1 C, it acts the same way. So 1 C for a 100 amp hour battery is a 100 amp drawdown. 1 C for a 1 amp battery is a 1 amp drawdown. But the batteries actually act pretty similarly. And that's why we use C rate so often, because it allows you to write characteristics for batteries regardless of how big and bulky they are. For example, if you look at the discharge current, if you're discharging it at 0.1 C, the final discharge voltage per cell, and again, remember there's 6 of those, is 1.75 volts. But if we were discharging it at 3 C, kind of the maximum end of this spectrum, it actually empties the batteries a lot lower. It drops them down to 1.3 volts per cell. And so, that's a pretty big difference of what is an empty battery. Well, what is an empty battery depends on how fast you're discharging it. Are you discharging it at 10% of its capacity, or are you discharging it at 3 times its capacity? And here's where it starts to get important to realize that, is because capacity actually changes with discharge rate. So I pulled this out of the manual, and you've got a 12 amp hour battery. If you're discharging it at something like, a 10-hour rate or a 5-hour rate, the effective capacity actually drops. And so look over here, if you're discharging it this much, it's actually only going to have, a capacity that's a lot smaller than a 12 amp hour battery. If you're emptying a 12 amp hour battery in 1 hour, you're only going to get 7.3 amps out of it. And so now we've really broken our gas tank analogy, because what I'm saying now is that if you empty your gas tank faster, your gas tank's going to be smaller. And if you empty your gas tank slower, you're going to actually have a bigger gas tank. So yeah, we've kind of broken away from the gas tank thought. But the idea behind this is that, you want to discharge your batteries as slow as possible, because as you slow down these charges, you're going to get batteries that last longer, and they're not going to get as low. So here's another chart showing what happens at different C levels. And again, this chart can only be made using C because it means that it's the same for any type of battery. And you can see that if you discharge a battery, sorry, I've got a little screen blocking my way. If you discharge the battery at something like 0.05 C, it's this number up here. It's going to last a long time. It's going to last 20 hours. And the final voltage is going to be around 11 volts. If we were to discharge it at something like 3 C, it's going to discharge in 6 minutes, and it's going to drop it all the way down to 9 volts. And so this is what I was saying. The faster you discharge it, the lower the voltage is. The other thing that's interesting to look at is that as soon as you put a discharge on the battery, it drops the voltage. But for something like a 0.1C or a 0.05C, it only drops it from maybe 13 volts to 12.5 or 12.4. As soon as this really high charge goes on it, as soon as you put 3C, it drops it from 13 down to like 10.5. So wait, there was something useful there. There's something we can get out of that. I said at 0.1C, it's going to deliver power around 12.5 volts, and 0.2C, it's going to deliver power at around 12.3. And I'm not going to go over Ohm's law. I promise this isn't going to be a math lesson. But if you had a 100 amp hour battery and you take like a 1 ohm resistor, that's going to draw about 12 amps, which is about 0.1C. And so one way you can actually test batteries in the field, if you don't have the time to do 20 hours of discharge and then 20 hours of recharge, is you can do this quick field test. And this field test doesn't necessarily replace doing a full discharge test, but it will allow you to get an idea of if a battery is good or not on a kind of shallow basis. Because if we put a resistor on a battery and it drops by a little bit, it's probably an okay battery. However, you've got to have the right current based off of the battery, because 12 amps is only 0.12C of a 100 amp hour battery. 12 amps would be 1C of a 12 volt battery. And so not only can you do this test, but you've got to make sure you have properly designed loads when you're doing it. So let's just kind of do an example. A battery starts at 12.8 volts and it falls to 12.35 during the test. So that test, we said it should drop to around 12.4. It dropped a little high, but then it recovers to 12.77 during the next 5 minutes or so. So the recovery was 0.42 and the total discharge was 0.45. The battery pretty much recovered everything it lost. If you do this test and the voltage drops to something like 12.2 or 12.1, or if the recovery is less than 75%, it's probably a bad battery. There are some caveats to this. If it's a hot day or if it's a cold day, or is it recently been charged, or is it a battery pulled from storage? But it gives you a basic understanding of how well your batteries are doing. One last lesson in physics before I change topics about this, power. So power is equal to I squared R. In our last example, we were drawing 13 currents for a 1 ohm resistor. So that's 170 watts. That's a lot of power, and it's only going to come out as heat. So if you think about the old, incandescent light bulbs, now we've got LEDs and fluorescent. But those old incandescent light bulbs, they're usually around 60 watts. And if you left that on for 5 minutes and you tried to unscrew the light bulb with your hand, it's going to hurt yourself. Now imagine something about 4 times that. These get hot when you're doing these tests. So just do be careful about those resistors, Don't put them anywhere that it can do damage with the heat. Don't grab it while it's going on, things like that. I'm going to try to share my webcam because I'm going to show you guys an actual discharge test. Let me see if I can get this to work. All right, I don't know how well you can see. I don't know if it's the full screen or not. Brad, if you don't mind jumping in and just letting me know if you can see it okay, or if it's just small.
It's small. It's up kind of in the top of our viewer window, but I can see your meter and your batteries.
Okay. I'm gonna see if I can make it the full screen, but if it gives me too much trouble, we'll just do the small version. Is that any better?
It looked like you had it for a minute, but then it switched right back to its view in the PowerPoint window, and then the little webcam up top.
Okay.
Now there's a way that I can enlarge it as the viewer. If I mouse over the webcam window and click enlarge, it actually just swapped the 2 screens. So now I can see your webcam a lot bigger. So for those folks that need to see it, put your mouse over the screen that has his webcam, go to the bottom right-hand corner of that. There's a button that pops up that says enlarge, click on that.
So what I've done is I've set my meter to volts. I've got two batteries on my desk. You can't really see both of them clearly, but I wanted you to be able to see the meter. I'm going to measure the voltage of this first battery. And it's coming back as 12.99. So it's a pretty well charged battery. But as I said, just measuring the voltage doesn't necessarily tell you the full story. I'm going to measure the voltage of this other battery. And it's 12.88. Again, a pretty fully charged battery, but we don't know if it still has the same capacity it used to have. So what I'm going to do is I've got a resistor, and I'm going to plug it into this back battery. So that was the battery that was at 12.88. I'm sorry if I'm bumping my microphone and making things kind of loud. So I'm going to stand up to do this. Hopefully I don't embarrass myself too much. We're at 12.88. I'm going to plug this in if I can do it one-handed. And you can see the voltage dropping now that it's plugged in. And it's dropped to 12.75 if you guys can't see it, 12.74, 12.73. I'm not going to sit here for a couple minutes because that would be pretty boring to watch. But I just want to show you how you can, see that battery voltage went down a little bit with the tester, and it's very slowly coming back up, but it's already back up to 12.77. Now let's look at the other battery. If I can get my hands on it. So this battery is at 12.99. So what's going to happen to that voltage as I put the tester on it? Again, I'm doing this one-handed, so it's a little clunky. What? At 12.99, tester's on it now. Look how fast it dropped. It's down to 8.5 volts. This second battery is completely shot. We started at 12.99 and putting the tester on for just a second, dropped it down to 8.4 volts. And it goes right back up. So it recovers okay, but it drops far, far too low for it to be an acceptable battery. And that's why you can do these field tests, because if you just were to measure the voltage, they look both like good batteries. But when we did the actual, the discharge test right there, the kind of field discharge test, we saw immediately that one battery was much worse than the other one. All right. Gonna go back to the presentation. Let me know if you have any issues seeing with it. Otherwise, I'm just going to keep talking.
You're good.
Thanks. So that's one way to test your batteries in the field. A few things about battery life. The deeper you discharge your battery, the more it's going to mess it up. Every time you deeply discharge your battery, you're effectively adding like more marbles to the gas tank every time. And so this graph is showing you that if you discharge it to a depth of 100%, you fully empty it, and you fully recharge it, it's only got about 200 cycles in it. If you only discharge a third of the battery, you're up to 1,000 cycles. So if you've got a site that's emptying out the battery every night, recharging it during the day, and emptying it out at night again, it's probably going to last about 200 to 300 days before that battery is just shot. If you have a battery that barely goes down all at night, you could last 3 or 4 years, no problem with that battery. The other thing that impacts how long batteries are good for is the temperature. So the hotter the temperature is, the shorter the service life is. So, if it's out in a nice 30-degree weather, this is 75 to 85 degrees, you can expect to get 5 or 6 years out of it. If it's really hot, if it's pushing 120, 130 degrees inside those metal boxes, you might only get 2 or 3 years out of it. So you want to keep your batteries as cool as possible when they're running. So generally speaking, best practices, you want to store your batteries in a cool environment, you want them charged, and you want them tested. When they're just sitting there on a shelf, so not when they're being used, but if you've just got them sitting there on a shelf, you can see that the storage period impacts the percentage of the battery, basically how full it is, based off temperature. So if you, for example, keep your batteries in your back shed and it gets to 104 degrees every day during the summer, it's only going to last about 6 or 9 months until you've already started to do damage to the battery because it's discharged so much. Meanwhile, if you, I don't know, decided to invest in an industrial freezer and you put them in a freezer, your batteries are only going to discharge like 5 or 10% in a year and a half. Now, this isn't very realistic, and most places aren't at 100 degrees 12 months out of the year, 24 hours a day, but it gives you an idea. The cooler you can store your batteries, not only will they last a lot longer at full charge, but it keeps it out of that danger zone. As soon as it's in this zone, that's going to start to hurt the battery. So you want to keep it relatively fully charged on the shelf. When you're charging a battery, you want that current that's charging the battery to be relatively stable until you reach that 13.7, 13.8 volts, and then you want the current to drop down as that battery voltage stabilizes. Any type of smart charger is going to do that for you, but you'll notice if you've just got kind of a wall power supply, that can actually kill your batteries as well. So the do's of batteries. You always want to charge your depleted batteries as fast as possible. If they're sitting there on the shelf, you probably want to charge them up every 6 months or so to keep them safe. You want to store those batteries cool, charged, and you want to have tested them before you store them. You want to charge and discharge as slowly as possible. And you can rapid charge it up to about 14.7 volts. And then you want to float charge it from there at about 13.6, which again, most smart chargers are going to do that on their own. The don'ts. You never ever charge a battery in an airtight enclosure. There's always the chance that that could lead to explosion and fire risk. It's a little bit less likely with sealed batteries, but it's still not worth the risk. So never charge a battery in something that's sealed and airtight. Never use a battery that looks like it's damaged. Don't exceed 14.7 volts if you're charging it. Don't let it drop below 12 or 10.5. Once you reach 10.5 volts, there's a chance the battery is never going to come back. And don't use just the voltage as battery health, because if we had done that on my example, the battery with a higher voltage would have looked good, but it was actually bad. When I say if it looks, damaged, you'll often see that batteries, when they reach the end of their life, or if they get heat damage, they get all swollen and puff out like this. At that point, just replace the battery. It's not worth trying to get a battery like this to work when you can replace it for $35, $40 and know your site's going to work. So a few common misconceptions about batteries. I can check the voltage to know if the battery is good or not. I think I've beat this point in enough, but no. Voltage only tells part of the story, and you need to do a discharge test to get the complete picture. Myth, I should always have a backup battery in my truck or toolbox. Oh, okay, that's mostly true, but just remember if it's in the, a toolbox in the back of your truck, it's going to get pretty hot, and remember what heat does to batteries. So don't leave it in your truck for too long, maybe swap them out once a month, put them back on a charger, and try to keep it in a place where it's going to stay nice and cool. Myth, a site that has a low voltage probably has a bad battery. Well, maybe, it might be a bad battery, but it could be a bad solar panel, it could be components drawing too much current, it could be a number of things. You don't want to just swap a battery because of a low voltage. Some final thoughts about batteries before I jump into solar panels. Batteries aren't complicated. This is pretty simple physics, but misunderstandings can cause troubleshooting in the wrong direction, and that just wastes time. So if you're working on a system with batteries, try to get an understanding of the basics of them. And then this is a link to the PowerSonic manual in case anyone wants to actually spend an hour of their life reading a battery manual, which I don't know who would really want to do that, but it is a good manual. All right, so solar panels. Let's do some work. Not real work, but physics work. In physics, work is equal to force times distance. That's kind of a mechanical definition of work. We kind of care more about the electrical definition of work, which is actually volts times amps times time. All right, that's getting confusing, but let's take a step back. If you look at your power bill every month, you'll see that you're getting charged per kilowatt hour. What you're actually getting charged for is the amount of work that the electricity did to run your house, to run your air conditioning, your refrigerator, your computer. That's measured in work, and it's measured in kilowatt hours. So how much work can you do with a Snickers bar? Well, calories are a measure of work. And so if you look at the calories and you convert it, the calories in a Snicker bar is about 300 watt hours. So with a 100 watt equivalent LED, that could run your lights for about 16 hours. Or it's about the same as two 12 amp hour batteries. So a Snickers bar could, run a gauge for a few months. It's the same as 772,000 foot-pounds. All right, that's a unit we don't see very often. But that'd be the same as lifting up a work truck 100 feet in the air. I don't feel like I can do that after eating a Snickers bar, but man, that'd be nice. You could boil 3 quarts of water. You could produce 1 million joules, or it's about 1 ounce of body fat, which just goes to show how much we need to watch what we eat, I guess. So work's important to understand as a concept, but what we actually care about in the field is power. And power is how quickly you're doing work. The basic unit of power is the watt, and 1 joule is 1 watt for 1 second. These equations that show you how to calculate the wattage are all just equations using Ohm's law. I'm not gonna jump into equations and expect you guys to do a lot of math, but if you just look here, power is equal to I, which is current, times E, which is voltage, or it's current squared times resistance, or it's voltage squared divided by resistance. Usually when you're measuring power, you just want to use whatever equation happens to be the most convenient for the numbers you've got on hand. So, okay, great. I just spent 5 minutes explaining work and power, and you've never really had to worry about that ever. Why does it matter? Why should you care? So let's look at an example. You are running, if you're running a flood warning system, or you're thinking about running one, you're installing sensors out there. And with these sensors, you've got long cable runs, sometimes 100, 200, 300 feet. So how do you pick which cable you use? And there's a chart over here, and this chart is comparing the wire gauge with its resistance per foot. Now, for those of you not familiar with wire gauge, the smaller the number it is, the actual bigger the diameter of that cable is. So a 14 gauge wire is a lot thicker than something like a 24 gauge wire. And what happens is with those thicker wires, you actually get less resistance because those thicker wires have more metal and more path for electricity. So you are losing power when you are setting these up, and you are losing power along those cable runs when they're longer. And that loss is proportional with resistance. So again, power is equal to I squared times R. So how much power is lost when you're running 100 milliamps through 300 feet of 24 gauge wire? All right, so we have current, I, and we have the resistance, R. So the current is 100 milliamps, which is actually 0.1 amps squared. And then you're gonna multiply that, we said it's 24 gauge wire, so that's 25.67 milliohms, which is why it's 0.02567, times 300 feet, and it's going both ways on that cable. So you're actually losing 0.15 watts. Not a huge amount of power, but something certainly noticeable and something certainly worth keeping in mind when you're building out your systems. What if it was the same situation, but it was 1 amp? So you're running 1 amp through 300 feet of 24 gauge wire. Well, 1 squared times the same resistance per foot it's 15 watts. Now you're losing 15 watts of power when you're doing that. You know, if you had a 20-watt solar panel, you're losing most of that power in just the cable itself. So again, you know, think about a 20-watt solar panel. And in this case, we're not going to do quite as long of a cable because you've only got 10 feet usually for solar panels. What power loss do you see on it? So using that same resistance, the total resistance of the wire along that 10 feet both ways is about half an ohm. A 20-watt panel is going to put out about an amp. And so if you do I squared, 1.2 times 1.2 times 0.5, it ends up being 0.72 watts. 0.72 watts relative to 20 watts, all right, we're only looking at a 3-4% power loss. It's not that bad, but again, it's something worth considering. And if you just use a better, you know, bulkier cable, it'll help with that. Or you just minimize your cable runs. You know, you don't want to be running 400 feet of cable for a solar panel because you're going to lose a lot of power with a run that long. So again, what does that have to do with solar panels? You know, all right, cables, watts, whatever, Mark, and why do I care? Well, solar panels provide power to charge the batteries. You know, you can have a gauge run off of a battery for a week or a month or a year, but at the end of the day, what's actually providing the power to these gauges is the sun. And so solar panels really are, you know, what drives any type of flood warning gauge. They're usually presented with their power in watts, and what wattage panel you need depends on the power budget. You know, think about what type of panels does your system use? Are you using 5-watt panels, 2.5-watt panels, 10 watts, 20 watts? These are things you've kind of seen, but maybe not thought too much about. So how does the solar panel work? You know, you've got power coming in and you've got basically 2 sheets of a specific type of, you kind of call it like a metal, but it's 2 sheets of a silicone. And again, not a physics lesson, but basically the sun's photons bump things around enough to cause power. So let's talk specs. Let's talk about what you would care about in the field. One of the things is called the open circuit voltage. So open circuit voltage is the peak voltage a panel can generate. It's the maximum potential that panel can overcome. So if you're looking at this graph, all the way on the right, you'll see VOC. That stands for voltage open circuit. Now power is equal to I squared times R, or E times R, or E times I. So power is equal to voltage times current. The voltage is really high here, but the current's 0. So no power is going to be generated here because there's no current. The other thing that panels will say is they have a short circuit current. And that's the current generated by a panel into a short circuit. All right, that makes sense. No power is produced here because your voltage is now 0. And so these two together create the IV curve, which is I is current, V is voltage. So you've got the current voltage curve of a panel. And you'll notice that that current is pretty much the same as voltage goes up. And then when voltage starts to get really, really high, it drops off. So where is the maximum power? Where do you have the highest voltage and current? Well, if you do the math, if you multiply the current times the voltage, you end up with this line, and the highest power occurs right around here. So right around here, where you've got high voltage and high current. So what do you measure on site? You know, if it's a clear day and it's around noon, you're going to get the highest values for your panel. And you'd measure the open circuit voltage, the closed circuit current, the output voltage from the regulator, the output current from the regulator. When you're doing that, you really want to make sure you've got the battery disconnected because the battery is going to, you know, influence the voltage that you're reading. So I'm going to try my webcam again. Let me see if I can just make it work this time. All right. So you're looking at my wall, which isn't very interesting. You can still see my multimeter, but outside I've got a solar panel, and that solar panel is still connected or still under sunlight. So if I take my multimeter and I take the 2 wires from it, I can measure the voltage. And if you can see it on the screen, it's measuring 19.23 volts. So that's going to be my open current or open circuit voltage. if I measure the current, it's going to use the same exact setup, but I'm going to change my multimeter to measure it in amps. So I move my lead from voltage to amps. I'm actually going to connect it the same way. So I'm going to put my negative on the negative and my positive on the positive. And you can see I'm getting currently 0.56 amps or 560 milliamps. It's a 10-watt panel, and so I would look up the spec sheet for that panel and see if I'm actually meeting the specs or not. I can tell you off the top of my head, that's pretty close. So all in all, that panel's working the way it should. That's what you do in the field. This is showing the characteristics for a 5-watt panel. And for a 5-watt panel, which is pretty commonly used in Alert and Alert 2, your open circuit voltage for this specific panel is 22 volts, and your short circuit current is 0.29. So we were about 20 volts, and we were about double this short circuit current. So at the end of the day, how much power can we get? And I'm not going to spend too much time on this. I know we're running a little short on time. But basically, what we care about is something called insolation, which is measured in watts per meter squared per hour, which just know that the higher that this number is, the more power we can get out of a solar panel. So this is a chart created that shows if you had a south-facing panel and it's tilted, how much radiation are you going to get, on average throughout the year. And if you're down in California or New Mexico and Arizona, you get pretty good. You're pushing 7 to 8 kilowatt hours meter squared per day. Okay, hard number to understand, but just know, you get more power in this part of the country and less in this part of the country. And this is looking at things not only like, its latitude and longitude, but also its cloud coverage and rain and temperatures and whatnot. So here's the solar radiation on average if you had a south-facing panel, but it was tilted vertically. So in the previous example, where it was kind of high, in this example, this is a panel that's kind of at 45 degrees-ish, depending on where you live. What if it was a straight up and down panel? If it's straight up and down, you notice there's a lot more greens and blues, right? You're only getting 2 to 3 of that value down here in like the Texas coast or up in the Pacific Northwest. And you're doing okay, but a lot lower. What on July? What if it was a vertical panel in July? I mean, look at the whole Gulf Coast. You're getting like 0 to 2. You're getting almost no sun on that panel during the month of July if it's straight up and down. So all that's to say, that's why we tilt our solar panels. Because the way the sun moves throughout the sky, if you can tilt your solar panel, you're going to get the maximum ability to charge up your sites. And so this is showing, the monthly average of that charging if you had a 90-degree panel or a 60-degree, 50-degree, 40, 30, 20, 0. So 0 would be a completely flat panel, and it's going to do great in June and July, but horrible in the winter. A vertical panel is going to do okay in this winter, but horrible in the summer. And a 45-degree panel, or depending on where you live, this is location specific, does pretty well throughout the year. That's why we tilt the panels. Looking back at batteries, remember how I said we want the battery voltage to top out at 13.7 and the current to drop down? We have a mismatch, right? Because I was saying that the panels are putting out 20 volts and they're going to put out high current all the way up to 16 volts. That's not what we want with a battery. That's going to hurt a battery. What we actually want is it to go up to about 13.5 and then drop the current. We want this. So how do we deal with this area of a mismatch? That's why we have voltage regulators. So voltage regulators, what they do is they protect the battery from overcharging. That preserves battery life and it keeps the voltages reasonable. It also prevents the batteries from discharging into the panels at night as well. And so when I was working on this presentation, one of the questions I had, and I kind of knew the answer, but I still want to know, well, why not just make panels that are 14-volt panels, right? And then they would naturally have that curve. And the reason that they don't have that is because that 20 volts is only promised during the best parts of the day. And so if you had a panel that was only putting out 15, 14 volts, Yeah, it might charge your batteries at noon, but at 8 a.m. and at 6 o'clock at night, good luck. If you have a 20-volt panel, then it's always going to have enough voltage to charge up your batteries. And then you just handle over voltages with a voltage regulator. Voltage regulators, they have spec sheets too. So I pulled this from a specific type of data logger, and then this is a 20-watt panel. What is the short circuit current of this panel? 1.16 amps. Or the current at power max, it's 1.12 amps. So this panel is going to put out 1 amp about, or 1.1 amps during the peak sun of the day. Look at this voltage regulator on this device. It's current limited to 0.9 amp maximum. That means if you're putting in a 20-watt panel into this device, you're out of spec. You're putting in too much current. This regulator can't handle 20 watts. So anytime you're looking at not only panels, but also your voltage regulators, make sure you read the specs because you want to make sure all your equipment's going to work the way it should. I mentioned power budgets. What are power budgets? And power budgets are a lot like finances. You can look at your incoming and your outgoing money and you can say, oh man, I'm spending too much. But what you really do is, oh man, I'm using too much power. And that's really all a power budget is. You take everything that's coming in, it might be a data logger, it might be a power amp, it might be a sensor, and you see what is the current, how often is it drawing that down, and you can do some fancy math in Excel and you can get, all right, this is what it's discharging per day. A power amp that transmits 150 times per day is going to draw down 208 milliamp hours every single day. Then I can say, all right, well, I'm going to be conservative with my solar panel. I'm going to say I'm only going to get 4 good collection hours per day. I might actually get 8, but in the morning it's not as good, and in the evening it's not as good, and there's a 10% chance of cloudiness. So you know what? Just to be safe, I'm going to say I only get 4 good hours. And I want it to be able to charge up twice what it uses in a day. My batteries, it might be a 12 amp hour battery, but I'm going to say I'd pull them once they're at 70%. So once it's dropped from 12 amp hours to like 9 amp hours, I'm not going to use it anymore. And I want it to run with absolutely no sun for, in this case, 38 days. If that solar panel gets stolen, how long is it going to keep the site going? 38 days in this example. And if you do the math with a power budget, it will tell you how many watts are required to run that site and how many amp hours are required for the batteries. So in whatever example I had pulled this from, it wanted a 3.3 watt solar panel and it wanted 22 amp hours of battery storage. Now, that's to run it for 40 days. Those are all designs that you put into your system. When you're building up a system, you say, all right, we know we get hurricanes and we get cloud cover for a week and a half. So I want my gauges to work for 21 days no matter what. Or you can, be in a place where you never see cloud cover more than 3 days in a row and you have a little bit more wiggle room. The advantage of a power budget is that it allows you to design your system to be the most effective and most efficient for the needs of what you're actually putting out there. So real quick, let's talk some issues. Look at this picture. That's an old picture from an agency that will remain unnamed. An old picture from a voltage regulator. Well, let's look at these. This wire, it's probably okay, but it might have been stripped too short. It might actually be crimping down on the insulation, which is going to cause bad contact. This one's a little too long. You've got metal sticking out there, and anything that hits that metal is going to cause a short circuit. And then in this case, the wire gauge was too big for this terminal. You've got stray little hairs sticking out there, and if these are touching these hairs, then you've got a short circuit on your solar panel. And so, anytime you're plugging something in, you might not have a bad panel, you might just have bad connections. Dirty panels. Very dirty panels can reduce power by about 5%, which isn't huge, but is noticeable. You can scratch your panel and that can cause long-term damage. Honestly, they just don't look as good, right? Your gauges are the front of your agency and you want them to look as pristine as possible. So you want your panels to look professional. And then heat is actually going to have more of an impact than this 5%. So if it's hot or cold, that's going to affect your panel performance way more than if they're dirty or not. Do you think hotter or colder panels work better? colder panels actually work better. You know, if it's a cooler solar panel, it's going to work a little bit more effectively than a hotter one. Last example, what's wrong here? So we're looking at data from 2013 to 2014. It's, you know, a year and a half of data. And this is the battery voltage. It starts high and it drops down to like 11.8, goes up 11.5, up 11.5, up, and maybe 11.8, up 11.2. What's going on here? Well, each time the battery goes up, this was a site visit that had been done to replace the battery. And so someone went out there and said, oh, the voltage is low, I've got a bad battery, put in a new one. 3 months later, oh, the voltage is low, I've got a bad battery, put in a new one. 3 months later, oh, the voltage is low, I've got a bad battery, put in a new one. And it went for a year and a half without the actual issue being resolved. And that's why I wanted to talk about batteries and solar panels today, is because if you don't have a good understanding of what's out there and how it works, you can fall into this trap of, all right, well, I fixed the problem, right? And then 3 months later, you're out there again, scratching your head, maybe forgot why you're out there the first time, and you're just doing the same work over and over and over again. And it's not efficient, and it wastes your time, and it wastes your manager's time, and at the end of the day, it's not a good way to run a system. What was actually going on here was two things. One, the solar panel gets very shaded during certain times of the year, and so the panel wasn't effectively able to charge up the site like the specs said it should. And then two, there was actually a weather sensor that was out of compliance. The weather sensor was drawing way too much current compared to what it said it should. And so what was assumed to be a battery problem actually ended up being a sensor problem. And taking the time to actually troubleshoot why your batteries are failing is almost as important as fixing the problem to begin with. So just some final things to know for system operators and technicians. Understand how your equipment works and read the spec sheets. Don't cheap out on power equipment. You know, a few extra dollars can save thousands of dollars worth of damage. If you're putting out a $5, a $10, a $20,000 gauge, you know, don't skimp out on $30 on a battery or a regulator because you think it'll make it work. You know, it's worth it to spend a couple extra bucks on your power systems so that your $10,000 gauge keeps working. New isn't always better for what it's worth. Most batteries have a measurable failure rate from the factory. You might get a shipment of 100 batteries and 5 of them fail within the first year. And that's kind of just the gamble you play with new batteries. And, you know, so if you get new batteries, kind of expect that you're probably going to have to replace a few of them once you've installed them. Consider the cost difference between solar panel sizes. You'll notice old networks have something like 2.5 watt panels. That's because 30 years ago when they were installed, those panels were expensive. The difference between a 5 and a 10 watt panel nowadays is usually 10, 15, maybe 20 or 30 bucks. At that price point, maybe it's worth it to get a slightly bigger panel because that gives you a lot more room for expansion and new sensors and new technology moving forward. So think about future-proofing your system a little bit by spending a few extra bucks on solar panels and batteries. And last thing is kind of what I just went on that last slide is make sure any troubleshooting discovers the root cause of the issue. And it's not just a Band-Aid that's kind of hiding the problem. You know, make sure you understand what is going on in the field, why components are failing or why they're working the way that they're working, and really spend that time to understand how your system works and how you can get it working the way it needs to work so that when it's raining, and it's been raining for 4 days straight, you know you're still going to get accurate, reliable, and trustworthy data. So with that, I will open it up to any questions you guys have. I know that was a bunch of information at once. As Brad mentioned, this presentation has been recorded and we're going to share it. And you know, I tried to squeeze it into an hour, but I'm happy to talk about this at any point if you guys have questions offline as well. But yeah, any questions from the group?
We did have one large question submitted. I'm going to paraphrase. Someone's asking about other battery technologies like lithium ion or anything like that. Are people using those for flood warning applications these days?
Yeah, no, that's a great question. So there's several different technologies out there for the type of batteries that you can use. You know, I only went over lead acid. Lithium ion is certainly becoming more and more commonly used. The thing about lithium ion is typically you are changing money for weight for the most part. And lithium-ion technology has gotten a lot better over the past decade, and I'm seeing it used more and more for these flood warning systems. But dollar for watt, you're still getting a lot more out of lead acids, and they're still just as reliable as long as you're taking care of them the way that you should. But I've noticed for things like IoT sensors and IoT flood warning networks, a lot of those have started to use those lithium ions because they're lightweight, they can handle a lot of the abuse, and they're getting so efficient and much more cheaper every year. But if you're talking about something that's a big battery and got satellite transmissions and radios and bubblers and stuff like that, generally speaking, lead acid's still a better way to go, just for cost. But ask me again in 5 years and I might have changed my mind.
Okay, we did have another question pop up asking, what is the difference between a cold battery and a hot battery?
Sure. I'm not sure I 100% understand the question, so I'll do my best. When I was talking about hot and cold batteries, I was in this presentation just referring to the actual temperature, right? And so batteries stored at room temperature are generally good for the batteries. Cooler than room temperature is always a little bit better. And then hot batteries, what I was referring to in this presentation at least is you go out to a site, and I'm in Texas right now, and you've got stainless steel and aluminum boxes, and you open that box and it's 120, 130 degrees inside that box. That's what I was referring to with hot batteries, is that those batteries being in those conditions will impact both the lifespan and the ability for that battery to do work.
Okay, we've had one more question pop up.
Okay.
Is there a noticeable difference in the efficiency of a gel battery versus lead acid battery in extreme cold temperatures?
That is a great question, and I don't think I'm qualified to answer that. I spent too much of my life in Texas, and other than this year, I haven't seen extreme cold for the most part. So I will, if you just shoot me an email, I'll happily get back to you, but I couldn't provide an accurate answer right now.
I've had a couple other comments pop up. This one says lithium batteries need different charge controllers due to the charging characteristics. That may be something that's why folks don't use those as often these days.
Mm-hmm.
And then another comment, northern latitudes, are higher capacity solar panels or larger AH batteries a more effective solution to low power issues?
Yeah, so real quick on the lithium, yeah, they do require kind of a whole different mindset of how you charge them. And, nowadays I'm seeing more and more people that will take, an order from China and like do lithium batteries to power their house, and they've got to do some work to make it work. But there's some pretty cool stuff going on there. For northern latitudes, yeah, you kind of run into two issues once you're further up. One is you're getting less sun during the winter, right? The further north you go, you might only get 6 or 7 hours of sunlight, or even worse. And then you also are typically cloudier during the winter as well. And so it really depends on your power budget to understand if you want bigger batteries or bigger panels. If you've got something that just doesn't take much power, you can probably get away with larger capacity to make it through the winter. On the other hand, if you've got something that you just can't necessarily easily keep up with that power, you might need the bigger panel so that on those days where it's nice and clear and sunny, you're getting as much charge into it as possible. But you are hurt by both the sun angle being lower, the sun hours being less, and more clouds. And so you often have to, beef up a little bit what you're doing. On the other hand, you often at northern latitudes are pulling up your PTs and doing a little bit less monitoring for flooding, at least, because a lot of times those sensors would freeze over.
Looks like the end of our questions.
Well, I appreciate everyone that got involved and asked questions, and my email's on the screen. I'm happy to answer any questions, or if you're curious to learn more, I'm always happy to talk, because as I said, at this point, I think I've got the reputation of the battery guy, but anything flood warning, I could go on and on. So I appreciate everyone taking the time today. Thanks.
Thanks, Mark. Appreciate everyone attending and hanging on for the extra time. And at this point, I'm going to terminate this webinar. So look forward to seeing everyone next month.
Take care.